Good evening, our supervisors and my colleagues. Today we are presenting our project, which is titled Design and Development of Proton, which is a smart solar electric utility vehicle for institutional mobility. This is a Group CS2633 project, and I'll be taking you through the first couple of slides. Proton is our attempt to solve a real problem on this campus, an affordable, intelligent, and solar-powered vehicle that doesn't just move people around, but actively monitors and manages itself while doing it. So let us start with a background. Makerere currently has no affordable, intelligent, and environmentally sustainable way to move people around campus. The vehicle in use today are inefficient, costly to keep running, and then add to environmental pollution. Where electrical vehicles do exist, they are typically just plug in to grid and offer almost no real visibility into how the vehicle is performing. No monitoring, no control, and that's the gap that Proton was designed to close. A solar electric mobility platform that brings together embedded control, energy management, communication, and real-time monitoring in one system. So let us move to the next slide. So related work and then our research gap. To understand why this matters, is we looked at what's already been done elsewhere. Electric vehicles have been developed worldwide, solar-assisted charging exists, IoT-based vehicle monitoring exists, and battery management systems are well established individually. What's missing is the integration, and particularly for African institutions where affordability matters a lot. So nobody has combined embedded intelligence, CAN networking, solar supervision, real-time telemetry, and battery analytics into one single affordable driven software system built for the campus environment. Proton answers that directly. On the hardware side, it's a hoverboard-based propulsion system paired with solar panel integration, a battery pack, embedded controllers, and the CAN communication modules. So instead of isolated components, you get one coordinated vehicle. The CAN bus architecture is a good example of solving that integration gap. We have 3 nodes, an ESP32 acting as a central controlling unit of some sort, and then a second ESP32 that's running the battery management system. And we know that handles servo control that talk to each other over CAN using MCP2515 controllers and then TGA1050 transceivers. That receives reliable communication, fault isolation if one node fails. So the modularity to scale up later, exactly the kind of integration architecture and the research gap institution mobility platform that what we are missing here. So what is our problem statement? So the gap is also what defines the problem, if I should say. Because nobody has built this combination affordably, Makerere has been left with vehicles people can monitor or trust. Proton's dashboard is direct response. It pulls real-time telemetry covering the vehicle's state, battery percentage, and voltage, solar activity, charging status, and then the CAN node health all in one place. In testing, that's not theoretical. It's pulling we get readings, things like 82%, battery percentage of charge, 35 volts, and solar marked active in real time. So let me hand over to our colleague to
Hello, everyone. Yeah, so this is Bob Kamli. Yeah, so first of all, I will apologize my camera. So I'll begin from where my colleague Joel has stopped. Yeah, and I will take you through the main objective. That is to design, develop, and evaluate intelligent software systems for Proton, which is a smart solar electric utility vehicle that enables sustainable, efficient, and intelligent mobility within campus or within Makerere University. Yeah, so due to time, allow me go to the next slide. Yes, so our next slide, yeah, so here now we have the specific objectives. The other one was the main objective, but now these ones are just specific. the development stage, the design and implementation, the part of integration, and also the part of evaluation or evaluating. So the management and monitoring system then meant the embedded control software for our vehicle operation. Yeah, so now going to the one of integration, the objective is to integrate the IoT capabilities for telemetry and remote diagnostics. So lastly, going to mean, here we evaluate system performance through prototype implementation and testing. Yeah, so those are the ones or the specific objectives we have got into our project. So allow me just briefly go through the methodology due to time. So under our methodology, we have the requirements, the system design, prototype development, module integration, system testing, and the performance evaluation. So under our methodology, of course, you have to first acquire the requirements, the one you need to use. Then after that, you have to design. After getting the tools, you have to design what are you going to work on. So from there, you develop the prototype. From building the prototype, then you have to integrate that prototype. Then from there, you have to test. Of course, for any system or for anything, you have to, that concerns software and everything, you have to test. And after testing, then you can evaluate your performance. Yeah, so allow me to call in my colleague to continue from there due to time. Thanks for listening and thanks for watching.
Good evening, everyone. And this is Sheriff, and I'll be taking you through the next slides. Okay. So the next slides, we talk about the system architecture. This is the architecture that we employed when we are developing this. And it starts at the top layer where we are having the dashboard. And this dashboard, it can be accessed via the phone or the laptop or the web interface, the way we designed it. So it connects to the CCU, which is the central control unit, via the Wi-Fi. And this CCU is just the brain of the system, which communicates to other modules. So below it, we do have the distributed embedded nodes, where we are having the servo nodes, the battery nodes, and other expandable modules, as you can see. Next slide, please. Okay, so the hardware prototype. It just shows you from here. You can just see a simple picture of how our hardware is. On the top, where we are having the solar panel, and at the base we are having the hoverboard, which is going to be working onto the propulsion. Then the battery pack, it can also be seen there, and the embedded controllers are also in there. Then the CAN communication module to be used through the wires. Next slide. Due to time. Okay, so this is our implementation of the central control unit. And here we are looking at the responsibilities where we are having the vehicle state management. In the vehicle state management, we are looking at the idle, then the forward and the reverse, and also implementing the left and right rotation or the turns. Then we are also looking at the stop and fault. We have the sensors which you have to go into that. Then CAN communication, this is communication between the different ECUs. Then the dashboard hosting, where we are seeing the dashboard and what is happening in. We shall discuss that in the next slides. Help me go to the next slide. Okay, the BPM, the battery management system, I'll just pass through it shortly. The function, it is implementing what we call the voltage monitoring, current monitoring, and the temperature monitoring. Then the state of charge estimation. This the state of charge is where it is assisting us to know, does the battery need to shift and we go to the solar charging, or shift and maintain the grid. Let me go to the next slide due to time. Okay, it's coming up. Then the CAN bus, this is where it is mostly used for communication of the different ECUs that are onto that we connected all together, where we're having the dashboard, the BMS, and the servos. Let me go to the next one due to time, because we are limited. Then I'll just briefly talk about the dashboard, where we are having the visual view of what we are seeing. So from what we are sharing here, the vehicle was in the stop mode. Stop mode is just like being idle. And our battery was at 82%. We look at the voltage, which was at 35, and it was active, it was on. That's all from me. Allow me to call in my colleague to take you through the last part of the session. Thank you.
Okay, thank you very much, Mr. Sharif. This is Derek Samuel Joga, and I'll be taking you through the last parts of this presentation. And we shall be starting from the communication testing, where we successfully established a communication between the various ECUs, that is the CCU and the BMS, and the CCU and the servo controller, real-time telemetry updates from the CCU to our dashboards, and the node health monitoring, where each ECU was having a heartbeat, and it was directly being tracked by our central control unit to determine that which one is on and which one is off. And then the system validation, we successfully demonstrated an intelligent vehicle supervision with battery monitoring, solar integration, and wireless telemetry, and a distributed embedded architecture where all major objectives were achieved. Then our results. So the results demonstrate the feasibility of implementing a software-defined mobility platform using low-cost embedded systems with key achievements including modular architecture, real-time monitoring, reliable communication, and solar-assisted energy supervision. Thus, our architecture provides a foundation for future intelligent mobility systems. And then our challenges, we had 4 major challenges, which included the budget constraints. The implementation costs exceeded our initial estimates. Then we had the lack of hoverboard documentation for the IC, which was on the hoverboard. It didn't have a publicly available data sheet, which limited our access to the controller internals. Then integration complexity, whereby multiple embedded modules required extensive debugging with, and lastly, which was the limited motor feedback, where we had to estimate the speed according to the time of the tilt of the IMUs on the controller. In conclusion, our Proton proof of concept successfully demonstrated an intelligent software-centered electric mobility platform with our achievements, including embedded vehicle control, battery management, CAN communication, solar supervision, and wireless telemetry. And thus, our project validates the feasibility of software-driven campus mobility systems around big institutions such as universities, hospitals, and airports, and big factories or industrial centers. Our recommendations: direct motor control using VESC, which is a certified and standard electric speed control for brushless motors. Then wheel encoders for accurate speed measurement and GPS integration, cloud-based analytics, predictive maintenance for the various parts and nodes, and full-scale vehicle implementation from just a mere prototype but to an actual vehicle. Thank you very much, and we'll be glad for any questions or comments. Thank you.